Howdy y'all, my name is Trenton Brendel, and today I will be teaching you about astronomy at the Large Binocular Telescope Observatory, which is a very exciting place to do astronomy. Here's an image of the Large Binocular Telescope. It's located up on Mount Graham, and it is one of the largest telescopes in the world. You may have noticed from the name it says binocular in it, and it does have binocular vision, just like you can see here. We have binocular vision with our two eyes. And these binoculars here also have binocular vision, and they will improve our ability to see things far away. Not nearly as good as the Large Binocular Telescope, though. The entrance aperture of these is about 2 inches across for each of the two sides, which is okay, but it's not great, and we could do a lot better. The mirrors that are used to collect light on the LBT, the Large Binocular Telescope, are 8.4 meters across, which is, for reference, about the size of a mid-sized school bus, if you've ever been on a school bus. Not a full-size school bus, but a mid-sized school bus. It's pretty big. And with those mirrors, we can collect a whole bunch of light, lots and lots of light. That's actually why we want such big mirrors, is because the more light we can collect, the more we can look at fainter and fainter objects that are further away or that are just dimmer in general to our vision, which generally means they're further away or they're giving off less light. Here you can see in this image that I've drawn a stick figure for scale. It's a little bit misleading because this is a very distorted image, but you can get an idea of how big these mirrors are and how big the whole observatory is. And again, it's a binocular observatory, so it has two sides, two primary mirrors, left and right, with optics, or things that look at light, overhead. In this case, they have a camera on the left, which is a blue camera. It looks at things in the blue end of the spectrum. And there's a camera on the right here, which is the red camera, and looks at things on the red end of the spectrum. But by having this two-sided structure, you can look at different ends of the visible spectrum, and not only the visible, but also the infrared, or like into the heat spectrum with other instruments at the same time, which is very, very useful for observers. Because sometimes you want to look in a broader waveband, but if you only have one instrument that has a certain band that it can look at, a certain range of wavelengths, and you're confined to that, then that's all you got. But if you have two sides at once, you can expand it much more. Very advantageous. Here is, instead of my stick figure drawing, a wonderful human for scale. And this just gives you an idea of how large this mirror is. This thing is 8.4 meters across, size of a mid-sized school bus, and it's very big. But you'll notice something else here that's really unique about this mirror. It actually has these structures inside of it. And these are honeycombs. They're actually ceramic casting cores, and they are used to lightweight the mirror. Here they're actually included inside of the mirror. But after the mirror is finished casting, which it is here, these ceramic cores are power washed out of the back. They use high pressure water and they blast it all out the back. And what you're left with is this, which is a mostly hollow honeycomb mirror. 8.4 meters, mostly hollow. If you were not to do this, if you didn't actually take this subtractive method of making the mirror and then removing most of the material from the inside, the mirror would be so heavy that you couldn't move it. You also wouldn't be able to bend it, which is something we often need to do in astronomy to make our image look better, as we bend the mirror up and down with a system called active optics. There's these forces, actuators, that push on the back of the mirror and wiggle it around. And you wouldn't actually be able to have the mirror change temperature quickly enough, which is something that's very important for astronomical observatories, because if you form a large temperature difference between the atmosphere in the observatory and the mirror itself, then you get poor imaging quality. You'll actually get like shape on the mirror that you were not anticipating and can be very hard to correct if you're not ventilating the mirror. And this is something they'll actually do, is they blow air into the bottom of the mirror through holes into these honeycomb structures to get the mirror to equalize with the surrounding temperature. So it's not experiencing what are called thermal gradients, and which is just a change in temperature over space, which is not good. We don't want that. And I should mention, these mirrors, these 8.4 meter mirrors, are made at the University of Arizona campus right here in the Richard F. Karras Mirror Lab, which is famous for making these spin cast honeycomb mirrors. A man named Roger Angel, who is a genius, came up with this technology, and it's one of the most groundbreaking things I think that has ever been done in optical fabrication ever, making of optics. Here you can see those ceramic cores being loaded and then glass being loaded on top of them inside of a furnace, and then the top goes down and the thing spins around. That's the basics of spin casting. Here's a closer view of glass being loaded on top. This is O'Hara E6 borosilicate glass, basically Pyrex for all intents and purposes, but a little bit different. Once that's loaded in, the top of the furnace is lowered down and the thing spins around about 7-ish times a minute. And while that's happening, while the spinning is occurring, the furnace is being heated and heated and heated from around ambient temperature to over 1,200 degrees Celsius, which I don't know what that is in Fahrenheit off the top of my head. Should have looked that up or just done the calculation, but it is very hot. It's very, very hot. You wouldn't want to touch it. It would incinerate you. But the really interesting part is when this whole process is done and all the glass inside the mirror, glass inside the furnace is melted, and you've got a nice parabolic shape, then it takes 3 months to cool down the mirror. This is a process called annealing, and if you do it too quickly, you'll build up stress inside the mirror. Nobody likes stress. Mirrors especially don't like stress, and they do bad things like break and deform and cause other optical defects when they are bending or releasing stress over time. Here's another view of that glass melting inside of the furnace. You can see it starts around like 6-7 inches of height, and as it melts, it forms a liquid state going through 900 degrees Celsius to 1,200 degrees Celsius, and then at the very end, you end up with about 2 inches, a little more than 2 inches of glass on the face sheet. That's the sheet between air above and the ceramic cores underneath. So it's 2 inches you start with. By the end of the whole process of mirror making, you're with about an inch left over. And people can walk on these mirrors, which I'll mention in a bit. It's crazy, 1 inch of glass. Just goes to show you how strong those honeycomb structures are. But before I talk about any of that, I'm going to demonstrate spin casting. So here I have a spin casting demonstration where I have a turntable right here, and then I have a bowl on top of it with water, which is evaporating as we speak, but it is still here for now. And you can see if I go ahead and turn this guy on, think of this like the furnace that the glass is inside of. The glass being liquid water here, but it could also be liquid glass if this was 1,200 degrees Celsius, but it's not because that wouldn't be very comfortable for any of us. But so you can see as I increase the temperature of the turntable, we start to get this curve at the bottom of the water, right? You see that curve right in there? And that's called the meniscus of the water, and it just so happens that when you rotate a cylinder with a liquid inside of it, it forms a parabola, a y equals x squared curve, just like this right here, y equals x squared. So the beauty of that is that effectively is a perfect mirror for astronomy because it forms a perfect point of light on axis when you focus light from infinity. All right, so now that you've seen how spin casting works with a demonstration, we can look at what the actual finished product looks like, or partially finished product. Here you can see a finished honeycomb mirror blank. Notice the word blank here. This is not a finished mirror because we still have to do optical surfacing on here, which basically just means we need to make it optically perfect. When we think about things in the optical, we're thinking about surface defects on the scale of microns to nanometers, which are small fractions of an inch. Like you can think of an inch and then think of a millionth of an inch, and that's like you're getting close. Here in this image as well, you'll notice that the ceramic cores are still in the mirror, and those have to be power washed out. They blast them out with water because ceramic, fortunately, is porous enough to be blasted out. And then you have essentially an empty or hollow mirror that has those ribs that form the honeycomb structure to give it rigidity. Once we've got that done, we'll move on to grinding and polishing, which is how we change the optical surface of the mirror. First, we'll do grinding with hard diamond tools that removes glass very quickly. And then we move to fine grinding, which is just slightly slower than that. And it should be noted that you're actually grinding both the front and the back of the mirror, because in order to get the nice contact on the back of the mirror to make sure you're putting the right forces into it, it has to be really flat, but not optically flat, just really flat mechanically speaking. But the front, we move to polishing of the front with things like soft pitch tools. Pitch is kind of like tar. It's really hard on short time scales. If you were to take a hammer to it, it would crack. But on long time scales, it'll flow. And that's the key here. You actually want it to conform or flow to meet the surface. And pitch, when you're using ferrous oxide to do polishing, will remove the glass very, very slowly, which is perfect for when you don't want to overshoot, because you can't put glass back on. You can only take it off. And if you do overshoot, you have to take everything else down, which can add years onto the project. These mirrors can take 5, 6, 7 years to make sometimes, which is expensive. So you can also, when you're polishing, to make sure you're putting the right shape into the mirror, the right local shape, you can use something called a stress lap, which is a really clever tool that they use here, that allows you to bend the shape of the tool you're polishing with while you're polishing. You can see actually some of those pitch pads right here on the bottom of the mirror. And those, again, are kind of like tar, but they're not tar. And by bending that tool as you're polishing, you are effectively able to control local surface deformation and, in effect, get a perfect mirror. Once you're finally finished with the polishing and the surface finishing of that mirror, then you can move on to aluminizing, which is actually done on a very consistent basis at the observatory using something called a bell jar. And this bell jar, we have one of them up at the LBT, is actually brought up to the telescope and clamped down onto the mirror cell. And they strip the old aluminized coating off that's covered in bird poo and all kinds of other things and dirt and old aluminum that you want to rip off. Clean the glass from there and then re-illuminize with the bell jar on the mirror. And that happens once every other year. On the other side of the mirror, in that same period of time, you'll be washing the mirror with a mop. People actually walk on the mirror, wash the mirror, and then they're good and get all the bird poop off. And you flip-flop every year. And that's how you keep the telescope mirrors in great operating condition. One of the beautiful things that I mentioned about LBT is it's very modular. It has a lot of different modes you can operate it in. I mentioned the cameras earlier, but there's more than just the cameras. So the cameras operate in prime focus mode, where you use just the parabolic primary mirror and then focus to a prime focus right here. And then there's also the Gregorian mode, where you use 2 mirrors, parabolic primary mirror, and then a concave secondary. It's a floppy mirror, an adaptive secondary mirror, to correct some of the aberrations from the sky above, or the defects in the image. And they focus below the primary. Just imagine this mirror is not here. And then finally, we have bent Gregorian mode, where we are able to take that focus from the secondary mirror and combine it with light from the other side of the telescope, or use another instrument, possibly in bent Gregorian mode. So to enact those different optical modes, we have swing arms. There are these black truss structures here that swing optics in and out above the primary mirror. And the first one we mentioned already, the large binocular camera, can be swung out here. It's actually out of the optical path now. Then we have the adaptive secondary mirror, which can be swung in. It is currently swung in. And then the tilted tertiary fold mirror. It's at 45 degrees, and it's currently swung in right over the primary mirror, where its swing arm actually hides behind the swing arm of the adaptive secondary. You don't want to add in shadows on the mirror if you don't have to, because that's obscuration, which is no good. And this mirror can be rotated to 3 different modes to get to these 3 different instrument ports at the center, which is where all the science instruments are located. The prime focus mode, you can see here in a little bit of detail. I mentioned that parabolic primary mirror only produces a perfect focus on axis, but as soon as you go just a little bit off axis, the aberrations start to come in, and you have to do something called a field correction, and that's what this lens system is for. It's a field corrector optic, essentially a camera for wide field imaging. It's not very wide, it's only a couple arc minutes, but which are fractions of a degree, so it's very not wide in our sense of the word, but in astronomical senses, it's pretty wide. Again, we also have the Gregorian mode with the concave secondary, focusing behind the primary mirror. And then we have a bent Gregorian mode where we insert that tertiary and we get an accessible focal plane in between the two telescopes. And as I mentioned earlier with these binoculars, this is a binocular observatory. So we can use this bent Gregorian mode right here to combine the light from the two sides together into a common focal plane with some relay optics, and that gives us effectively a 22-meter baseline. So it's like we're using a 22-meter telescope, which is huge. That's really big. I don't have a reference. Think of that as like 2 buses back to back, which is one of the biggest advantages of using the LBT. And here are some of the beautiful images that have been taken with LBT. This is actually a commissioning or first light image. Early on back in 2005. Many of you were probably not alive then, maybe. Here are some other images, the Crab Nebula. Here's the Pinwheel Galaxy and the Ring Nebula. And you can also see some images down below that are a little bit small, but they illustrate the ability of the telescope to combine light from two sides and put it together into what's called an interferometric mode, where they take light from two sides, interfere it, and get these wavy fringes that give you more information than you get from just one side alone. And here's a view of the Milky Way over Mount Graham. So, thank you for attending.